Sorry, we're getting a few different technical difficulties causing some problems. And some of the basics we're going to cover today. So for the new users, we're going to cover kind of the foundational components of how you would use the performance measures and really how we can apply them. So, I mean, normally I don't get into too many slides, but today's going to be a little bit of a slide heavy day, and I will get into Traffic Link as well. But feel free to ask questions in the chat along the way. But in any case, for those that don't know me, my name is Brent Rogerson. I'm an ITS sales engineer on the Myovision sales team. I've been with Myovision for a number of years now, and get to spend a lot of my time with all of our customers, helping them take advantage of the products, using them, applying them in different ways, and maximizing the value out of it. So I do get into a lot of content. I do recognize that I kind of move pretty quick through this. So if you have questions along the way, as I was saying, feel free to message in the chat window. I'll just open it up that I can see that. There we go. Yeah, I can see the chat window. So if you have any chats or if you have any questions, please let me know as we go, and I will try to leave some time at the end to answer a few questions. But if I don't get to your question or don't answer, please still message and I'll follow up with you after the session, or feel free to contact our sales support team or even your local distributor that sells Myovision products. So, like I said, it is a little bit content heavy. We're going to get back to the basics. I'm going to cover quite a bit of the charts. We're going to go through them individually and work our way through some of those items. And at the end, I have a quick little customer use example that I thought was really interesting. I thought it was really cool, so I'll quickly cover that as well. So, understanding ATSPMs, automated traffic signal performance measures, and just to quickly, I'll take one slide to do this, is just to really understand the concept of why we're using ATSPMs. These performance measures are supposed to change the dynamic a little bit on how signal timing actually occurs. And traditionally, it's a spot study based, or an engineering firm would come in, they do a study, you'd provide a timing plan report, and then every few years you would update this report and kind of continue on. What ATSPMs actually provide is a more iterative approach, a reduced delay. You can monitor it constantly, and you can really make small tweaks to the timing over a longer period of time and make those iterations occur much quicker, so that the general delay of updates is actually much faster, and the public actually sees the signals actually change more appropriately, or change more alongside the developing road or the community, whatever it may be. So the whole purpose of utilizing ATSPMs is to decrease this delay in updating of timings and using real performance measures to make those changes. Myovision provides quite a bit of tools to accomplish this, and they're all slightly used for different reasons and for different purposes. So I'm going to try and go through a lot of them today and make sure we cover some of the foundational components of each one of these charts. Let's hit that slide. One thing that I always wanted everyone to be aware of, and I'll try to send this out to the user group following this session, but Myovision does actually have a guide to automated traffic signal performance measures. It's a book called Clear Signals. We sent it out as a webinar campaign probably 2 years ago now, and it was heavily geared towards similar topics I'm going to be talking about today. I've actually taken some of the slides from this document, or from this guidebook, and it really shows, it breaks down each one of the charts. It covers the importance of maintenance health, operational health, signal optimization, and then even how to measure before, after of those elements. So I definitely encourage you to look at it, read through it, see if you can take advantage of any of the knowledge in there. It's quite action-packed with great information. So we're going to get to it now. We're going to work our way through each one of these charts, and I'm going to be kind of doing it in order of where the data is coming from. And it's important to know how these data elements come together. And many of you may have actually seen this slide before. I've used it quite a bit. I've talked to many users with this slide deck, because once you understand the foundational components, where data comes from or how data is being used or applied, it helps with the context of actually getting information out of the system and how to actually read some of those charts. So there's three main sources of data that we use in the ATSPMs. The first one, probably the obvious one, is your traffic controller, the signal status. It lets us pull phase timing plans, all the various like PET inputs, anything that's going into that traffic controller, we can pull typically over NTCP, so typically directly from the controller itself. Then next is the detector activation. So whether it's myovision detection, loops in the ground, radar, whatever it may be, this gets inputted to the traffic controller. So again, while we're reading from the traffic controller, we're also combining the detection inputs and the signal status, and that actually allows us to drive at some of the major feature sets like split failures, split trends, occupancy ratios, all in relation to the signal status. The last one that I'm going to touch on a little bit is actually the Wi-Fi travel time probe. So as many of you know, our antenna for the device does have a Wi-Fi travel time probe built into it on the top of every traffic signal. That means you can measure point-to-point travel time. We can do what we call the congestion scan. It really helps us construct where problems in the network simply derived from the actual travel time of the road. So where does it spike? Where does it change? Where does it slow down traditionally throughout the day? And then combine that with the other data sources, we end up with a nice range of data to review. So quick little chart. I know this may not have all the context just yet. There are quite a bit of charts, but you can see a little bit of how they're being combined, and different charts are derived from different sources of data. And I have a few more slides that actually break this down a little bit further. But as an example, one of the major features that I focus on, or that we utilize quite a bit in our tools, is the split failure. And it's basically what this chart is telling us. We need the signal status and the stop bar detection to derive this chart. Then there's other charts like Purdue coordination, which is about the signal status and the advanced detection. And then we can go further with things like red light runner, where we need the signal status and the turning movement counts. So there's a combination of all the data inputs that actually drive at each one of these charts. And here, I'll break that down a little bit further. So there we go. So the first one, kind of basic concept, we'll go through the travel time. So there's two major charts that are coming from the travel time charts, or the travel time data. The first one is the point-to-point travel time chart. This is really what it sounds like. It's two different points on a map. You click on them and it derives instance of travel between, in terms of travel time, so between 2 points. And then it plots them on a chart so you can see throughout the day what are the general travel time. It being a Wi-Fi mechanism, the yield rate of this data is typically around, I would say, 10 to 16%. Most people have Wi-Fi on their phones. Most people are utilizing Wi-Fi in some way. That's why we chose to use Wi-Fi over Bluetooth. But when you do that, that means out of all the traffic on the road, we are still capturing about 16% of all those vehicles, which gives you kind of a representation of what the general traffic is. It's not the whole picture, but it certainly gives you enough of the idea to look at an overall trend. Similar to this little image here on the left, when something spikes, say there's an incident on the road, or a road temporarily is blocked because of construction, whatever it may be, you see a spike in travel time holistically. So you see that across more than one car, more than one incident, and typically for an entire time period. So utilizing a point-to-point travel time between two particular points can allow you to, one, understand the 24-hour median and all the individual instances, but it also helps you assess variability to that. And that's the last point here, is variability of travel time is an important element. How consistent is it? Is that a normal day? What is the typical 80% variation, 90%, 95th percentile? and how variable is that type of data if you were to compare that across multiple, say, Tuesdays or multiple Wednesdays, how consistent is that variability? And that would really help out with understanding the relative or the relative use of that data, or how it compares over time, so that you can make the right decisions from it. The next one, I think I skipped one there. The next one that I wanted to actually quickly highlight was the congestion scan chart that I may have, there we go. The corridor heat map, or the congestion scan tools, kind of contextualizes that across multiple intersections along a corridor. So on the left there, you're seeing what we call the heat map. And what it's showing you is basically top to bottom so top to bottom is southbound and bottom to top is northbound, and then each band is actually representing the relative distance between each intersection. But when you compile that across the entire day, across an entire corridor, you actually get basically a scan that shows you where in the network is it slowing down. And so when we actually look at where it could be slowing down, it actually can point to where the problems may be. So it's a good way to understand where a problem is before you start getting into the timing diagram side or the timing plans itself. You don't necessarily want to go look at two intersections that the travel time is actually working fairly successfully across. You would want to look at where in the network is it actually breaking down, and that could point to things like coordination problems or offset problems. Could mean that general amount of time is no longer enough. Could mean that, say, like a Costco was installed or built nearby, and it's kind of changed the dynamics of the corridor a little bit. You do see some funny examples of this from things like Black Friday or even like Christmas time. You'll start seeing some variations of this throughout the general week, but it's a nice handy tool to understand the general success of travel time through corridor and pinpoint where it could be breaking down. So let me go back to this one. So the next one is more about just the controller itself. So before we get into the combination of some of the data, the traffic controller does provide some pretty useful information on its own, main one being just the phase interval chart. Phase interval chart provides you with what was the length of the green, what was the length of the red, what was the length of the yellow across all movements of the intersection, mainly to highlight generally what is it doing throughout the day. Many cities run time of day plans, AM, PM peak periods, where they actually shift schedules. And when that occurs, you want to be able to just simply see, is that happening? Is it working as expected? And then you can simply toggle through the timing of the time of day plan. So if you expected it to come on at 7 a.m. And say the length of the green changes for the AM period, does it actually do that? You can simply check that in the phase interval chart. There's then, similar to that, the green allocation chart, which illustrates that distribution of green time allocated to all phases over a 24-hour period. So if you're actually looking at, say it's an intersection that's maybe running in a fully actuated mode or even a semi-actuated mode, how much green time is actually being allocated to each phase throughout the day, and is it dynamically working the way you'd expect it to? The last chart, PED delay. This comes from the push buttons in usually just directly wired into the cabinet, so not normally is the input coming from another source, but from the controller we can start seeing some of this combination effects of how long are the pedestrian signals up, how long are people waiting between pushing the button and actually getting to cross the road. So some basic information around how much time is being allocated simply for the PED phases. And these just generally come from any traffic controller. We often collect it through NTCIP, the Ethernet connection. It also can come from SDLC as well if you're only connected over the one source, but it really helps you assess how well is it operating without detection inputs. So we'll go to the next one. So signal status plus the stop bar detection. This is where the data gets really interesting, or at least starts to get pretty interesting. One of the major concepts that our traffic engineering team focuses on, and one of the major items really assess success of progression or the demand at the intersection being served properly is the concept of a split failure. So to get to a split failure, and we're going to talk a little bit about a split failure for the next little bit. It is a big concept in how our tools work and where some of even our intersection health alerts come from. And over the last few months, I think I focused quite a bit on talking about intersection health without really talking about what is a split failure. So first step in understanding the split failure is understanding the occupancy ratio chart. The occupancy ratio chart is somewhat what it sounds like. It's calculating the percentage of time that the zone is occupied during the green phase, during the red phase, and most importantly, the first 5 seconds of the red phase. If you end up with a scenario where, say, the green phase, so the green part of the phase has, say, 100% occupancy for the entire duration, and then as soon as the light turns red, you still have occupancy percentage in the first 5 seconds of red, that is what we call a split failure. That means the demand wasn't served properly. There was too many cars, it was oversaturated for that particular approach, and it allows us to see how often that is actually occurring throughout the day. And so if you do that at every zone, for every movement, for every phase around an intersection, you end up with essentially a count of how often the split failure is occurring from the occupancy ratio itself. So if you can see there on the bottom right, there's a split trend chart, which actually highlights the frequency of various types of detector use and detector occupancy. To help break that down a little bit more, because this is an important topic, I do have a couple more slides here that break it down. So load for me. There we go. So we talked about the occupancy ratio, but the split failure is what I want to unpack a little bit more. So this chart on the left, shows each one of those circles is a plotted use of the detector, a plotted phase. So what that means is the green occupancy percentage over the red occupancy percentage in the first 5 seconds. So say as an example, blue here on the left, bottom left, is where we would classify a particular phase as having spare capacity. The green occupancy percentage of utilization, so the amount of time that the zone was occupied during the green phase, is less than 60% of the time, and the percentage of vehicles being left over when the light turns red is below 60% as well. That means there is a fairly low utilization of this particular zone during this phase, and you generally have spare capacity, and that's what blue means. Blue means spare capacity. If we look at the green one, so the bottom right side, this is when when the zone itself, its occupancy is high during the green phase, but when the light turns red, there is very little cars left over, meaning you're adequately serving the demand at the intersection. When you do that, that means it was a successful use of the phase. We want the timing to be allocated in a way that you can really maximize the time that's being allocated, because there's other movements at an intersection. So if you think about a left turn here, we have the eastbound left turn being highlighted here. You want your left turn phase to be fully utilizing the green time with no one left over at the end, which means the rest of the time can go to the through movements or opposing movements that needed as well. The next one, top left, is the random arrivals. This one's a little bit harder to time for, hard to plan for, because they're often coming from side streets or coming from side streets, or they're coming from, say, malls, or just very randomly. They're not a commuter-like effect where you see like AM, PM peaks. It's more so random. But really how you measure this is that the occupancy ratio during the green phase is less than 60%, but then you have a high occupancy during the first 5 seconds of red, meaning randomly there's people there as soon as the light turns red, and it's hard to tell where they came from. We call those random arrivals. Where it starts getting, when it becomes something that you really want to start watching, is how many times we see this top right quadrant, the purple and the red. So the purple is really what we traffic. This is 60 to 100% of the time that detector is occupied for that phase during the green phase, and then similar to that, there's always vehicles left over in the first 5 seconds of red. So you're getting a much higher traffic volume, or you're getting a little bit more saturated, but it's not quite failing to 100%. And that's where we see red split failures. A split failure really occurs when you're in that range of 80 to 100% of the green phase is occupied, as well as 80 to 100% of the first 5 seconds is occupied. And that's really indicating that the demand wasn't being served. And then you take that approach for every movement around the intersection and assess how often is that actually occurring around the intersection. This really helps us assess at an intersection layer, so a single intersection, not necessarily the entire corridor, but it really helps us understand how successful is the timing working at this intersection. So I'll jump to the next one here. So from there, we actually created the split trend chart. The split trend chart is probably the one that I use 80% of the time to understand how well an intersection is moving. It basically just tallies that up throughout the entire day. It looks at every 15-minute interval. I'm not sure you can see that on the left there, but the percentage of cycles that have been classified as there was a split failure, heavy traffic, it was okay, random arrivals, or spare capacity. How many cycles can be tallied up that fall into those indications? And then you can really start seeing how well each movement is handling the demand. And then you look at that across multiple intersections and multiple movements across the corridor, and you can start really assessing where time could be reallocated. And that's really where our intersection health alerts, if you're familiar with those, that actually derive at phase termination issues, suboptimal green splits. And what that may be causing is, like the most obvious one is probably your phase termination issue, which we talked about when we went into the intersection health tools. It really breaks down how often are phases not terminating properly because they have too much time, or they're just going to the maximum time all the time, and you see a lot of blue, versus how many movements at an intersection, or how many times does an approach just not serve the demand, and then actually alert on those through the intersection health tool. So we rely on this metric quite a bit for our intersection health alerts, as well as our understanding of the progression. So there's more. We can go further into signal status, advanced detection. When you have a little bit more sensors at the intersection, so we have the controller, we have the stop bar detection, and you can have upstream or advanced detection, you can start layering in a little bit more information about some of the platooning effects, the approach volumes, or even just those percentages of arrivals on red that come from vehicles that are about to arrive on red, not necessarily they are there on red. And that comes from the predictive side of the advanced detection, really understanding who is approaching the intersection. With the Purdue coordination chart there on the right, it really gets you, it really allows you to see that platooning effect. So the grouping of detector hits, the grouping of cars approaching the intersection, and really seeing how is those platoons arriving at one intersection and then getting to the next intersection and working their way through a corridor. Very often I'll see, say, like major roads coming off of a highway, platooning becomes a super important effect. If they come from a free flow off ramp or free flow movement from a highway, and then they come up to a red light, you can start actually platooning them into the city and start pushing them through a corridor in a more controlled way, because you can see the platooning effect. And then you know the expected volumes at each intersection because you have a control mechanism at the top of a corridor working their way into the intersection. So it all depends on the intersection design, but really getting the layers of data points here is the concept. Really understanding how many people you're trying to serve, how many vehicles are in the network, where are they arriving at the intersection, and how well is the signal accommodating that time. And that's where something simple like a detection for actuation can create extensions based on volume, or it can run essentially through the night in a way that it never places, it never cycles to another like minor movement, because there's always demand on a major movement. So that's the whole purpose of having detection, is really to optimize in between some of these factors. So as many of you know, with the MyOvision system, with our traffic link and our SmartSense device, it does do traffic counts, as well as a couple more handy charts that are in the list there. One of the two big ones here are the red light running and the pedestrian compliance. So similar to not just looking at the timing plan design, or not looking at how well is the vehicle traffic being served, but also understanding where maybe when there's not enough time, how many people are actually trying to run the red light, or how many people are trying to run the yellow to get through because of maybe a timing problem. Similar to that with pedestrian compliance, how often are pedestrians jaywalking? How often are they crossing the road when they shouldn't be? And that could all relate to the other charts about not getting enough time, not being allocated properly, and then people trying to rush the signal or cross the road when they're not supposed to. And all these factors come together to look at an intersection more holistically. So we have all these charts in our system to help you really understand all the different angles of data coming from this traffic controller, the signal, the turning movement counts, and the video analytics that we provide. But you're probably thinking, that's a lot of data. And this is where some of our sessions around intersection health comes in. We really help you through one of our analytics charts or through our intersection health tool, really try to conceptualize this in a way that you can view where to look, where to go, which intersection is causing the problem. And it could be something simple like the time-space diagram, where the coordination is breaking down or the offsets are breaking down. It could mean that the platooning effects are not working, things like that. But in any case, one of the major tools here that's on the right is the intersection report card, which you may be familiar with. The report card tool allows you to look at the major metrics of approach volumes, split failures, split trends, and really assess percentage of change. So you don't necessarily always want to go looking for a problem at every movement of every intersection. You really want to be looking for which intersections are changing, which ones are impacting a corridor, which ones are people complaining about, which is often where we start. But with the report card tool, you can really monitor percentage change at an intersection. So as neighborhoods develop, or as say a Costco gets built, really what has changed in the neighborhood that has caused the change in traffic. And then you want to start looking. And so that's what the tools are really trying to help you with, is get through that data and highlight more problems in a way that you can actually solve them. Let me get out of here. So I'm going to just play around with a couple charts over here in Traffic Link. Hopefully this loads up for me okay. Just bear with me while I get logged in. Often I hear from our users that sometimes it's hard to really know where to start, or what some of the foundational layers of the data really are to really get into them. And so what I'm hoping to accomplish today is really address that, is some of the, where's the data coming from, what are the charts supposed to be used for, and then generally how do I just use them, so that if you go off following the session today to go maybe try something on your own, or try something in your data, maybe you'll be able to get there faster, and you'll be able to ask some better questions about what's happening in your network. Let's go to me, anything is in my way here. Sorry, I'm just jumping to a better spot to show you some data. Just waiting for it to load. I'm running on a pretty slow computer right now. Jump into this org just to show some really fun data. And I often jump into the platform in these sessions so that you can really you can really see how to interact with it, because that's the main point here. So let's go over, let's pick an intersection as an example. Let's use this one. And my screen is looking a little zoomed in there. All right, so along the left here, when you're logged into your TrafficLink account, along the left, you'll see your Insights button. You click on Insights, and now some of these things may starting to be clicking a little bit. So load up Insights. We'll go over to our workspaces. So workspaces is really where everything is built around an intersection set of charts. So this is where you can really build your analysis out. We call it workspaces on purpose, mainly because we want you to be able to save your workspace and come back to it later and really, and really iterate on your charts. The whole concept of ATSPMs is really allowing for iteration. So let's first look at an occupancy ratio chart. So we're looking at a single intersection here. We want to pick the particular movement that we care about. Let's call northbound through. We can look back at essentially any of the days that we've been collecting data for. Click on the 12th, which is yesterday. I'll hit apply there, and then it'll load up our first chart. And so you can see here immediately it's allowing me to add a second chart. Maybe I picked an intersection that won't have any fun data. Of course. And go back to a different intersection. Oh, I picked the wrong one, that's why. And we'll load up. Just gonna grab this. There we go. Hopefully it's not lagging too much on. All right, so let me load up this intersection set of charts. And we will rebuild those ones. I'll quickly clear out the ones I already had. Delete those, and we'll create a few here. And so we want this intersection, we're going to look at the occupancy ratios again. Take one of the particular movements. We'll let that load up. There we go. So we get one of our charts here. So this is the occupancy chart. You can zoom in by just highlighting over the map or over the chart itself. And so you can go right into a particular time period. So if we do want to look at, there we go. Say if we want to look at a particular movement, we're looking at westbound through movement here. You can toggle the charts. And so say we want to look at just the green occupancy ratio. We can see that throughout the whole day, the red occupancy ratio, and then most importantly, the red occupancy ratio in the first 5 seconds. So this is the basis of that chart that really helps us contextualize a particular movement, but really the one that starts tallying it up and actually gives you a real sense of what's going on. And then, well, which one were we just looking at there? Southbound through. We'll pull up the split trend chart here. And then it tallies it all up. So really now we can see, again, the same concept I was talking about earlier, spare capacity, heavy traffic, split failure, random arrival, and then okay, or being used adequately. You can really see how this particular movement tallies up through the entire day. And then we can really understand where there is spare capacity. So even here in the morning period, right around the 8 a.m. peak, the timing looks appropriate and looks like it's being allocated. But then there's right into 10 a.m. there's a lot of spare capacity on the through movement. But that's only telling us one piece of the story when we're looking at a single movement or a single event. We do want to understand it from multiple movements and essentially the entire intersection. And so when you're doing that and you're building it, you can add each one of the charts to really unpack how does this holistically work. The other one I like to do for that same concept is over here right underneath the Insights button, the Analysis tab down. I'll click on that. It does that to some degree for you. So there's an intersection option here where you can configure an analysis. And one of the charts that you can add in here for this particular movement is the split trend chart. So now we can look at that same data set, but it will actually pull all of the movements automatically for you. So that you don't really have to go in there and create each one. This isn't like a workspace where you can save the workspace and come back to it later. You have to actually like create your analysis each time that you want to do it on this side. And so you could go and create this on the workspace, save it, and then just iterate it over there. Or if you're just looking to quickly check particular movements or particular times of day, you can just go over to the Analysis tab and pull it up. So here we can now look at all of the movements around the intersection. Maybe let's pull this in a bit, take a different time frame. So this slides a bit over here. And then it gives you a little bit of a closer look at the intersection itself. So you can see how like the southbound through had some spare capacity, whereas our westbound left is well oversaturated. The eastbound, the westbound through is fairly saturated. You can really get a sense of where is there extra time. There's not actually much extra time at this intersection, but maybe the concept makes sense now. And so you can really look at that. Just check to see. Okay, we're doing okay here. So with that said, let's go back to analysis, or sorry, to our Insights tab. And there's a few more in there that we can quickly create. And then I'll wrap it up with a fun little story. Part of what I'm hoping that happens is I challenge you to go out and kind of try some of these charts, look through some of your intersection help alerts if you have them, start creating some of your own workspaces around some of those problems and see if you can derive at where the problem is anywhere in the network. So I'll go back to this page here. And so now you can see how each one of those charts could be created. You can click on them, select your time period, and open up the charts for any particular movement. I'm curious now because there is some pretty high use on some of these approaches, pretty high saturation. I wonder if that stuff gets reflected into red light running at the same time. So now you can start getting the combination effect of what's causing what at the intersection. And well, yeah, look at that. So this is our westbound traffic. And so if we actually switch this chart, you can go back and you can edit any one of these charts at any time. So let's look back at that westbound through. So each one of these charts now is westbound through. And we're somewhat combining some of the information here. And so now we can see that on the westbound through, the occupancy ratios on red and green are super high. Split failure counts between 3 p.m. and 6 p.m. are super high. And it's also starting to get reflected in the red light running charts as well, which means we're in the red light running charts. What this is measuring is when the vehicles are in, where they are in the intersection in relation to the signal. So are they running the yellow light, the all red clearance, which is usually 2 to 3 seconds, depending on how you have it programmed. So you have that all red part of the sequence, and then you have your normal phasing. At this particular intersection, we are starting to see some people stretch into about 8 seconds past when the light turned yellow. 7.3 seconds, 7.4 seconds. That means people are running into saturation. They're starting to push their way through the intersection because they need to get through. That could potentially lead to a safety hazard or just a good indication that people are pushing the signal a little bit, which could trigger a retiming. So combining these factors, you can really start seeing the behavioral impacts of what a signal timing can actually cause. If it's not timed well, there's not enough allocation around the intersection. Vehicles will start pushing their way through, causing the intersection to become slowly unsafe over time, and causing people to call in with complaints, and nobody wants that. And so feel free to start combining some of these factors. The whole purpose of the intersection help tool, which is this last piece here, is that you don't really, we recognize that you don't necessarily have all day to sit and look at every one of these charts. What the intersection help tool does is it really pulls it all together for you. I don't know why this zoomed out way far from me. And it starts highlighting improvements or particular intersections that are exhibiting signs of phase termination issues, suboptimal green splits, or imbalanced intersections, as well as poor progression quality along a corridor. And so it highlights some common problems over a 30-day period worth of data. So it has to be pretty persistent in the network as a problem, and it will highlight it in a way that it will be more visible, and then you can go and address those problems directly. That way, if you don't have the time to check through every chart, so you don't have the staff, just follow your intersection health alerts, look what the data is telling you, maybe try and make a change to the intersection or a small tweak that may resolve the problem, and then in the next month, see if the data reflects that change. From there, what I love to do is show that change and that impact in the report card tool. The report card tool is 100% a before-after tool. It's really just looking for what was it and what is it now, and what is the percentage change across your network, the corridor, and the intersection itself. And if you haven't seen this before, it gives you some pretty handy information like level of service, total vehicle delay, the travel time along corridors, some normalized reliability. So it really gets you a nice cross section of which corridors are changing, which one have the highest delay, and what is the general level of service that's actually occurring at the intersection. And so I use this after I start with a problem, say with the intersection help tool, go to the charts, deconstruct the problem, figure out what you can do about the problem, potentially go out and make a change, and then monitor that change in the report card tool. And if you combine all of those factors together and that workflow together, you really end up with some positive outcomes along the intersection. And I mean, obviously, if it doesn't create a positive outcome, you can see it almost immediately. Say it didn't quite go the way you expected it to. Revert the change, monitor the data again, and then try something different. The purpose of ATSPMs, again, is to allow for that iteration, not ongoing major studies. So combine those together and have some fun in your intersections. So I'm going to go back to the presentation here now, and just about a quick story from one of our customers. This will load up. Let me just see if there was any questions in the chat box here. There we go. All right. Why it's taking so long to load? I can jump down to where we were. All right. So I'm going to talk about a quick customer use case, simply using the travel time and count information. I find this a very powerful story, just from a couple perspectives. Present this so it goes bigger. Sorry, it's taking so long to load. So what this story was about was it was essentially around utilizing the travel time charts and the in the overall counts and assessing a major change to a traffic problem. And what that can mean is really looking at deconstructing the impacts that actually occurred. So one of our big customers and a group that we love to work with is Escambia County. I'm not sure if they're on the call here, but I'm sure they're interested in the story as well. It's their story, but graciously they let me talk about it today. And so right near the Gulf of Mexico, Hurricane Sally hit pretty hard, and it was pretty rough for the area. And you can kind of see some of the impacts through this story here. But one of the major impacts that did occur was the damage from the hurricane actually caused one of the major bridges between the major downtown area and more of the vacation area near the beach, and where all the tourist attraction or the tourism actually goes to, which is a major route between the two. And so closing this bridge is a fairly substantial decision. And when it got damaged in the hurricane, some detour needed to be created to mitigate that travel change and give time for that bridge to be repaired and open back up again. And so what happened with this story basically is that bridge had to get closed, and really we wanted to monitor if there was any changes to the time patterns or what that overall impact of that issue was in and around this area. And you can see there's a couple detour routes that go back around to the main area of Pensacola, and there's one that goes all the way around back into Pensacola as well. And luckily MyoVision was installed at some of these major inputs so that we can actually measure some of the travel time and the counts along the way. So first, let's look at the volumes. This is a good way to contextualize actually what's going on there. And so when we look at the turning movement counts, the total daily volume was around 25,000 vehicles on a typical day. When the bridge got damaged and it got closed, the volumes dropped to about 10,000. And that means that there were still people in the area while the bridge was closed, and then they worked their way around that long detour route, but generally that intersection was no longer utilized. And you can see the chart of volumes there at the bottom where we see about the 25,000 drop to almost about 10,000, and throughout the duration of the bridge closure, all the way up until about May 2021, you can see the volume stayed pretty low. And then once the bridge reopened, the traffic started going back, and then the expected volumes were returning. We can even see a slight increase now, now that everyone heard the word that everything was open back up again and everything was back to normal. Even more tourism arrived following that, which really indicates to the public that now is a good time to go. And so you can really monitor the volumes of that impact of just when that bridge was closed and when that all occurred, just through the general turning movement counts as well. So when you actually look at the travel time impacts to that, there is if you just look it up on Google Maps, the expected travel is was actually occurring around 13 minutes across the commuter route. And so between April and May, when the bridge is closed, the travel times doubled along this corridor, along this commuter route or the detour route. It almost doubled. And then when it came back to normal, we're starting to see the 12 to 13 minutes, which was the normal time. So normal time, again, about 12 to 13 minutes, which is indicated on the green average there that we see on the chart. And then when the bridge was closed, the blue line spiked. We were seeing up to about 27, 30 minute round trips around that detour, which is a significant impact of travel time. But when you don't really have many other options, the bridge was closed, it kind of is what it is. But then you can start measuring what the impacts and how people are feeling about that, and maybe potentially come up with other solutions to how it could be managed. And this is where you're really getting into demand management of vehicles. You can see that there's a spike in the morning and a spike in the evening. If the public was aware of this extreme travel time and this change in patterns, then it can start to be normalized. So instead of everyone coming at 7, maybe they can start coming at noon when it's actually more normal, instead of all trying to get through the same corridor that just wasn't built for the same throughput. And so that's something that could be taken away from this, as well as that's maybe as the backup plan, maybe that needs to be built and expanded on in case this happens again. But at the same time, you can almost manage the demand and start normalizing it. One of the really cool things that Escambia Beach did was actually public on their public portal actually present the current travel time and present the current conditions in a way that the public can see that, react to it, and actually normalize it for themselves and plan around some of these detours, which is a great amount of communication from the city to the public about how to manage these situations while the city is really trying to fix the bridge and get everything back to normal. So it helps you manage the demand quite a bit. Oh, a little too far now. So just to build on that, and I'll only take one more minute and then I'll wrap this up. Generally, like we see the travel time and we see this type of impact in the data, but what does that mean for the everyday driver, or what does that mean to the public? And you can really start using some of the FHWA quantifying charts and some of the calculators that the FHWA has provided to really show us the impacts of traffic signal timing and throughputs. And there's two major calculations. One is user cost, so really the deriving at how much time people have had to spend in the cost of user time, fuel costs, keeping the cars in that corridor longer, having them stop more, and then ultimately the CO2 that was generated because of that. And so we really want to, put in programs to reduce some of those things and really quantify those impacts. And so when as an actual driver on the road, you want to know what that impact was to me, and that means it's my time and the cost to be in the car and things like that. And that's why I personally would want to normalize it and understanding when these spikes are occurring so that I know when to avoid them to keep my costs low. But then when you contextualize that across 13,000 vehicles with approximately 1.2 pedestrian or passengers in each vehicle and the price of gas for an extended period of time, about 150 days, with this increased travel time, you can add up the direct cost to the public. And in this case, the cost was actually around 2.3 million that was impacted by this. So that's a real substantial amount. And one of the more important one was the fuel cost consumption there. So in the future, now that this data exists, it could be better mitigated, or at least it's known, and more programs can be put to mitigate some of those costs. In comparison, so this is actually looking at the northbound travel, so trying to get from the beach back into the main city, and that's really comparing the throughput on that side. When we look in the other direction, it was about half as much. It wasn't nearly as bad, because once everyone is in the city, getting back to the city is a little bit more spread out. The spike was more near the PM period when maybe people are coming back from dinner, things like that. And the volumes were a little bit lower because many people live in the city or live on the other side, not on the beach. And so the impact was a little bit lower. And then when you combine the two effects on both sides of the roads, you can really see what the impact of travel time can have on the general public and the general consumption of fuel and time. So it's a really fun way to quantify the impacts through just simple travel time and count information along a corridor. And total cost of the bridge closure to the public was about 3.6 million. So a really exciting way to look at the data, and a really great story about how data could be applied. Okay. So that kind of wraps up my content today. I'll see if there's any questions in the chat here. I don't see any questions, but anyways, so we covered quite a bit today between all of the different charts that are available, how to combine some of them together between between the signal statuses, what the impact of travel time does, and a fun use case of how that data was applied and how that impact to the public actually can be quantified. So the data is really powerful, it's really helpful. I would be really interested in exploring some of these data points in each one of your TrafficLink orgs and how some of this could be applied. If you're interested in running an evaluation with myself and our traffic engineer, Olivia, please reach out to us and let us know. We'd be very, very excited to do that with you and really unlock the power of performance measures. So there's no questions in the chat here that I don't see. Great. I'll give everyone the rest of their day back. So thank you so much for attending, and hope you all have a good day. Thank you so much.